Okay, so we'll restart then. All right, so let's see a few more properties of the integral, and we're going to start looking into a bit more surprising things. Right? A part of what we're going to do was already kind of visible, because part of what we're going to do is we're going to think of the integrals not just as a function or as a sort of a functional or as depending on the function they receive, but also sort of as a functional of the arc in which they're defined. Right? Over the reals, maybe it wasn't as interesting to do that, right? To integrate was an interesting operation that you could see what it would do to different functions, but it wasn't necessarily that interesting of an operation to fix a function and try to understand what the integral does to different sets when you integrate over those sets, right? However, here there's much more richness in the different arcs and that you can consider, and so it becomes a much more interesting object to just sort of fix the function and think of the integral as a function of the right, as a function of the arc in which is defined. Okay, my Zoom crashed. Actually, everything crashed, it seems. My local recording crashed. Let me see if I can fix everything. Okay, good. Thanks. Someone told me YouTube is still working. Let me just kickstart my local recording. Let's do another one. Zoom seems to be fine. Okay, so yeah, I'm not quite sure what happened, but right, perfect. All right, great. Okay, sorry for the, yeah, I was saying that because of the richness of the sort of the different arcs we can define integrals over, it's actually going to make a lot of sense to think of the integrals as a function of the arc, right? And this is going to give rise to a lot of understanding of geometry of arcs and of spaces and so on, okay? So before we get there, let me just, one thing that will be useful too is to consider an integral with respect, right? We're going to consider integrals with respect to the conjugate, right? So what I mean by this, it will make sense to consider things like this. Right, and so I mean, the natural definition for this is just the integral of the conjugate of the function, right? And the conjugate twice, right? You would expect that, you know, if I were to conjugate twice, it should be the same as nothing, and so this conjugate should cancel with this one and just leave it here, right? So this makes sense, and we're going to see how it, you know, it's pretty compatible with many things that you would expect would hold. And in particular, once you do that, you start being able to integrate also only with respect to say the x variable or the y variable. If you think of right, if you think of z as I plus a, as x plus, right, we oftentimes think of z as x plus iy. Right, that's sort of the notation we've been using a lot. Then we can also now start talking about the integral of f with respect to x. Okay, this is all over some arc. Right, and so this should, of course, just be 1/2 the integral with respect to dz plus the integral with respect to the conjugate variable. And if I integrate with respect to the complex, right, part, the imaginary part, then, right, it should be 1/2i of the number minus its conjugate, right? So, right, these are things that okay. Okay, now if we have that f, let's say that f of z, right, is equal to u of z, right? Or again, z we sometimes write as x plus I y. Right? Sometimes it's useful to, you know, go back to the real variables to see a few things. So we'll do that now. Plus I vz. Right? And it's not hard to see, right? If you use these definitions and just, you know, expand everything and cancel out a lot of integrals, it's not hard to see that the integral fz dz, right, is equal to the integral of, right, imagining, right, expanding here, expanding dz, right, in dx plus I dy, then we get that, right, this should be this minus v dy plus, right, the imaginary part should be, so v dx plus u dy. Okay, and of course you can now, right, you can define the integral in the way we defined and define the integral of the conjugate this way, right, and then dx and dy this way, or you could have just, defined it this way and get all those properties, right? It doesn't really matter which one you do first, right? It's a matter of taste. But here, let's say we define it this way, but then this, you just, if you were to expand everything out, you would get exactly what you would expect by just expanding these two terms. Okay, and sometimes it's also useful to integrate, right? We're still doing a lot of definitions. To integrate with respect to length, right? And so this we mean, we sometimes call this integrating f with, when we say with respect to length, sometimes we use the variable s, so you'll see this a few times, but really the right way to write it, I think, would be to do something like this, right? We do it with respect to the length of the interval, right? Not just the derivative with direction. And so this would be, right, exactly, right, f of zt times the absolute value of the derivative dt. Right, so it's an integral where, there's no cancellation sort of from the path going around or coming back or things like this. Is a very different integral, right? But we'll see how sometimes it'll be important, right? It's also independent of parametrization, right? I won't prove that because it's exactly the same calculation. Independent of parametrization. Right, provided that you're not, that your parametrization doesn't go on the path up, right? Provided that you're not allowed, right? It needs to be a regular representation. You're not allowed to do things like go up and then in the same path consider it same part of the arc, but go down in the parametrization back up, right? The parametrization should be so that this is never zero. Okay. But here, because we are integrating with respect to length, right? In particular, this absolute value, if you go and see the proof that when we took the integral over the opposite arc, we got minus the arc, right? Basically, the minus is going to disappear inside this absolute value, right? If we integrate with respect to just length, it doesn't matter which direction we integrate, right? It will still be the same value, right? So over, when we do it with respect to length, we have that the integral over an arc is the same one as the opposite, as the integral over the opposite arc. Okay. Okay, so in particular, if I have this, okay, and I won't prove this, but you just redo the calculation, and you notice that by putting the absolute values there, you'll see that right, that the minus doesn't come out, right? So this is the same as integrating against the arc, right? There is no minus sign. Okay. There is also a triangle inequality, sort of exactly the same one, right? I mean, right? An important triangle inequality is that the integral, right, the normal integral of f dz, right, is smaller or equal than the integral. I mean, this is sort of clear, but it's worth writing. Right, the normal integral of f of z is always smaller or equal than the integral where I do it over the length integral rather than the normal integral. Okay, so it's this form of triangle inequality. Okay, So I think now we're almost done with definitions. Okay, let me just make sure. Okay, so now we're going to start thinking of integrals, right? So line integrals, or path, or arc. Right, we can think of them as function of the arcs. Okay, and let's for a second now think of the complex plane in the variables x and y, right? Just so that we go back to a bit of normal real analysis, or real calculus, and we'll start seeing some, right? We'll start seeing some surprising properties. Okay, so let's say I have a region. Okay, let's say that we're doing everything in a region, right? Open and connected. Okay. Right, it's a region of the complex plane, and I can think of it either in variables in terms of z, a complex number, or just x and y, as where z is x plus iy. Okay. Now I can start thinking of things like the integral over a path, right, of p, let's say, of course, receives variables x and y, right, and I integrate with respect to x plus, sorry, its imaginary part, q receiving again, right, x and y dy. Right? I can fix p and q. Let's say p and q are continuous in omega, right? And I let arc sort of think of it as free to vary in omega. Okay, so I have some set omega, and I'm now taking some arc in it, right? Okay. And of course, right, this could just be, p could just be the real part, say, and, right, or if you think in terms of the other integral, p is some now complex function, right? And q could be some also complex function or integrating over the real part and the imaginary part, right? So complex integrals will be able to be written in this form, right? And in particular, to not keep track of all the p's and q's, I'm going to write oftentimes things like this. Okay, but of course, what I mean is I have some path in this region of the plane, and I'm integrating a function over the path, and I'm separating the part that integrates with respect to x and with respect to y. Okay, now an interesting thing, and sort of this is where sort of surprising things start arising, is that sometimes, or I should even say, well, let's say sometimes. Okay, sometimes the integral of alpha depends, the integral of gamma depends only on the endpoints of gamma and not on the arc itself. Okay, so sometimes if we think of these integrals, right, I think I fix p and q, I have now this dx plus q dy, right? Sometimes these integrals, as a function of the curve gamma, turns out that they'll depend only on the endpoints of gamma and not on the actual arc, right? So sometimes will be the case, right, whereby sometimes, I mean, for some choices of p and q, it will be the case that if I have an integral over a curve gamma, and I have another integral over another curve with the same, right, let's say, gamma prime, then the integral over gamma prime will be exactly the same. And this will be key. Now, before I go and explain and we try to sort of investigate when this is the case, this might already remind you of something, right? Which is over the reals when we have a primitive, right? When the integral is just equal to the primitive at the endpoint minus the primitive at the beginning, if something like this is to be true over on integration over the plane and the complex numbers, then you certainly expect this, right? Because the integral, both of these integrals should be the value of some primitive, right? We have to think about what a primitive really means here, minus the value of a primitive here, and therefore it shouldn't depend on how I actually traveled there, right? And it turns out that complex functions, analytic functions, will satisfy this property many, many times, right? In the sense that they will have a primitive in this sense. And this will be key for a variety of reasons, one of which, maybe was one of the main reasons why complex analysis was important in the beginning, is that it will actually allow you to compute integrals over the reals that were quite hard to compute without this idea. Because if I have this something like this being true, then I can think of one curve as just being the reals and taking a function that's very difficult to integrate over the reals, right? But if I can take another path that goes over the complex numbers that might a priori seem more complicated, but for which the start point and the end point is the same, then maybe, just maybe, actually over the complex numbers, I can integrate such a function easily. And I know because of these type of considerations that the functions are the same, the values are the same, right? And this is the idea of computing so-called contour integrals and the contour integral method and so on. Okay. So what we're going to do for the rest of today is explore when is it that, for which properties of P and Q do we need so that this integral depends only on the endpoints of gamma. And then we're going to try and see what if P and Q actually arise from a function taking values on the complex plane. What is it that this function needs to satisfy in order for its integrals to depend only on the, right, for its integrals to depend only on the start and end point. Okay, so I think we're all done with definitions pretty much. Well, almost. And we can start investigating properties and proving theorems. Okay, sure I don't forget any definition. And I'll have to do it. Okay. Okay, so what we want to understand is when is it that the integral, right? When I'm gonna stop writing p dx q dy, but I mean the integral, right, over some function. When is it that depends only on the endpoints of gamma, right? So I will say that the integral, right, depends only on endpoints. Okay, let me see. Maybe I should make this more clear. Fix, right, P and Q, so P dx plus Q dy, right? The functions P and Q are fixed, right? And now we after we fix this, then we ask this question. So the integral depends only on endpoints of gamma, right? So let's see what we can say. So if it depends only on the endpoints of gamma, what happens if gamma is closed? Right? If gamma is closed, right? Then if gamma is closed, the integral should be 0. Right? Because if gamma is closed, if it's sort of that intuition that, you know, we start here and then there, right? Let's say we fix. Then if it's this intuition that it should be the value at the end minus the value at the beginning, then it should be 0. Okay, I haven't actually proved it yet, but I will. Right, so if it depends only on the endpoints, it should be that integrals over closed curves should be 0. Okay, but in particular, we're going to show that this is if and only if. If and only if equals 0 for closed gamma. Okay, so let's prove it. I mean, I've already given you sort of the intuition, right? That this should be coming because, you know, some function at the end minus some function at the beginning, and so of course it should be 0 there. Okay, but how do we prove something like this? Okay, so proof. Okay, so let's prove first this implication, right? So it depends only on the endpoints of gamma, then it needs to be 0 for the closed curves. Well, this is easy because gamma and minus gamma have the same endpoints, right? This means in particular that the integral of minus gamma is the same as the integral of gamma. Right? Maybe I'll write integral of gamma is the same as the integral of minus gamma because they have the same endpoints. Right? But the integral of minus gamma is minus the integral of gamma. Right? So for a number to be the same as minus the number, they need to be 0. Okay, so far so good. Let's prove the other implication. Let's say that the integral for any closed curve is 0. Then can we show that it depends only on the endpoints? So let's say gamma 1 and gamma 2 have the same endpoints. If that's the case, then gamma 1 minus gamma 2, right? If I have a curve with the same endpoints, say this is gamma 1, and now this is gamma 2. Right? If I take the curve that goes gamma 1 and then back on minus gamma 2, it's a closed curve. Right? So gamma 1 minus gamma 2 is closed. Okay, and now if that's closed, then it's clear, right? Because the integral of this is 0, and it's the integral over gamma 1 minus the integral over gamma 2. Okay, let me erase here. All right, so an easy property without sort of having to use any analysis. But a very important one. It's closed. Yeah, go ahead. Let me just finish writing.
The path is closed as well.
For the first,
I think it should be clear, but
I'm saying okay. I'm saying closed. If like say take this. Okay. I'm trying not to write a lot, but take gamma closed. Right? So I'm trying to prove, right? I'm using the fact that it depends only on endpoints. I'm trying to prove that it's 0 for closed paths. So I'm now saying take a path that it's closed. I'm going to prove that it's 0. Right? Because the path is closed, the path and minus the path have the same endpoints. Right? Otherwise, if it's not closed, they don't. I mean, as a set, they're the same endpoints, but as a list, they're not, right? Because they're swapped. Right? So take a path that's closed. Gamma and minus gamma have the same endpoints, right? Because it's like A twice, right? Both of them. And because of this, then they have to have the same integral. But we also know that the integral over minus gamma is minus the integral over gamma, so it must be 0. Right? That's the proof of the first implication. For the second implication, I take two paths that have the same endpoints. If they have the same endpoints, then the difference is closed. If the difference is closed, then the integral is 0. But this is the integral over gamma 1 plus the integral. Right, sorry that the board is a bit dirty on the bottom, but let's say is the integral over gamma 1 plus the integral over minus gamma 2. But this is just the integral of gamma 1 minus the integral over gamma 2. And so because this was 0, these two numbers need to be the same. We're done. Okay, thanks for the question. Is it clear now? Yeah, if not clear, please, yeah, go ahead and interrupt. Okay. Okay, so now we're going to prove a theorem that makes this, that will make this intuition that, right, they should not depend on the path and depend only on the endpoints, basically if they have a primitive, right? So this theorem is going to tell us exactly what one means by this primitive, right? It needs basically for there to be a function defined on the plane whose partial derivative over x is p and whose partial derivative over y is q. Okay, so let's prove one of the sort of the main theorems in understanding this before we move to the complex, right, to the actual complex functions. Right, so the line integral or the path integral, right? Let's say. Remember, p and q are functions of x and y. dy, right? Right, defined in the region omega. Right, depends only on the endpoints of the path, right, which is of course inside omega, if and only if there exists a function u of x and y, right, defined in omega. Okay, let's say, I mean, p and q should of course be, p and q should be continuous. I'm always assuming that these functions are all continuous in the region. Right, if there is a function defined in omega such that, right, the partial of the function u with respect to x is equal to p, and the partial of u with respect to I is equal to q. Right, this will behave like a primitive. Okay, let's prove this theorem. One of the implications is quite easy. The other not quite as easy, but also not so hard. Okay, so the easy part, of course, is that if such a function exists, right, if a primitive exists, then of course the integral can only depend on the endpoints, right? So let's do that one first. Right, so let's say that such u exists. U exists as described. Right? Now we can take, right, let's take the integral over the path of px p dx plus q dy. Right? But what is this? This is just the integral, right, over the path. Right? We can now think of the parameterization of the path AB, right, of the partial of u with respect to x, right, at point xy, Now, the derivative of x, right? Because the arc now, right, I'm defining it basically as, right, x of t, y of t, right, which will be like the real part and imaginary part, but for now I'm not putting complex numbers in yet. Okay, plus the partial u with respect to y prime of t, right, now dt. Okay, but this is just the derivative, right? What's here is just the chain rule, right? It's just the chain rule for the derivative of u. Right? Because if I take the derivative with respect to t of u, I get the partial derivative of u with respect to x times the derivative of x plus the partial with respect to the second variable times the derivative of y. Right? But this is now an integral over the reals, right? There's no path, there's nothing. It's just over an interval over the reals of a derivative. And this, by the fundamental theorem of calculus, we know that it's simply the value of u at the end of the path minus the value of u at the beginning. Right? And so we're done. Well, for this implication at least. Right? Because regardless of the parameterization, the endpoint and the start point need to be the same. Okay, and so this depends only if such a function u exists, right? This depends only on the value of the function at the endpoint minus the value of the function at the beginning. Right. Now, we need to maybe make a point that maybe, right, this function u exists, but maybe there are more than one, right? In order for all of this to be well defined, right? Maybe the function u I pick could depend on the parameterization, right? But it's clear that if u exists, it needs to be unique up to a constant, right? Because its derivatives are fixed. So the only freedom it could have is a constant, is adding or subtracting a constant. But if we add or subtract a constant, right, it gets added or subtracted in both of these, and so it cancels out, right? So the u is unique up to a constant, and that's all we need for this expression to be well-defined and unique. Okay, so let's do the other side of the implication. It's a bit more interesting. Okay, so proof. Okay, so let's use the same notation as we had before. Okay, so we have that this is a region. Right, so it's open and connected. Okay, P and Q is continuous. Okay, so now the idea is that, we're going to use so what's the strategy here, right? I'm going to try to define the primitive of this P and Q, right? So I'm going to try to define it as an integral of something. Now, I have trouble, right? We potentially could have trouble defining it as the integral because, right? So before I do the proof, let's think about what's going to happen, right? I'm just going to define basically u as the value of the integral on the curve so that something like this holds, right? Now, in general, it could be that it's not well defined because it might depend on the curve. But if it doesn't depend on the curve, then it means that it's well defined, and that's basically all I need. right? So as long as the integral depends only on the endpoints, I can define u basically as the integral, right? As the integral over a path that joins to the point xy, and this is well defined, right? Just because we are wanting the partials of x and y to show up, and we know all these terms for integration over just the interval, right? We're going to define it over polygon lines, but we know that any region is connected by polygon lines, and in particular, we can pick these lines to be right, horizontal and vertical. So okay. So now let's do a drawing to see what's going to happen. Fix some point xy, x0, y0 in omega. So let's say omega is something like this. Okay, let's say this is omega. Okay, so fix that. Now I'm going to define u and y. Now take some point xy here. Right, the idea is that I'm going to define, right, so before we actually do it, I'm going to define u of xy as the integral, right, as the integral starting here and going up to here over the arc. Right, so I'm going to define basically u xy just as the integral over the arc of p dx plus q dy. Okay, but now I have to show that I can do this properly and that the derivatives are the right one and all of that. We'll do that in a second. Okay, but this is going to be the idea. And because it only depends on endpoints, this is well defined. Now, of course, it depends where I start, right? It depends on the x0 and the y0. But, right, this is just a constant. If I move it from somewhere, if I start from somewhere else, I just get a different additive constant on u, right? We know that u is like a primitive, is defined up to an additive constant, right? Because when I differentiate on the constant, it becomes 0. Okay, so now I can pick a path, right? We know that because it's a region, it's connected, that I can pick a polygon line path. So let me pick a path. Let me do the following. Let me pick a path that's just horizontal and vertical lines, right? It's not hard to see that you can do that, right? Then let's say that the last line coming out will be horizontal, right? I can always do that too, because, right? I can always do this because the set is open, so there is a ball. There is for sure a ball around my point, so I can always make the last line be horizontal. And let's say that I do this now, right? Vertical, another horizontal. Okay, so I have some path. Let me call this like gamma x. So now if I look at what u of xy is, I can take, right, so this is xy. Let me take another point here. We do it with another color so that this is more visible. Let me take another point here. Let me call this point x prime, y prime. Right? If I define u, the integral now over that, right, doing it over gamma or doing it over gamma x is the same. So this means that u of xy, right, is equal to, there's some constant, which is the integral that goes from here until the point x prime, y prime, right, plus the integral, right? Now, y is actually fixed, right? Y prime is completely fixed. So basically, this is just the integral from some x prime to x, right? The dy, y isn't varying. So this is just, okay, I need another dummy variable. Let me say that I'm trying. Let me write here big X maybe, just to just so that I don't have to define x double prime, okay? So I'm making this be big X, okay? Okay, is it clear? Let me say it again. Maybe I should, yeah, just because, I mean, otherwise a bit of abuse of notation to use the same letter for the dummy variables as, okay, so this is the point xy big, and this is the point x prime. I mean, we do this all the time, right? Using like the same names for different variables when there is no risk of confusion, but maybe it's better this way. So like the big X and big Y are the points, and the small x and small y are just going to be my dummy variables at the moment, okay? Right, so I can define u in this way, right? The integral of a path that goes to a point xi. But in particular, now if I do it over the blue point and I fix some point x prime y, right? Then all I have, and I take the parameterization that just parameterizes sort of at speed 1, right? That parameterizes it by this part of the arc is just parameterized by the normal interval from x prime to x, because I can pick any parameterization. Then the function is equal to some constant, which is the integral up to here, right? Plus this part, but this part is equal to the integral from x prime to x, right? From big X prime to big X, right? Of pxy dx. But then by just, by just fundamental theorem calculus or just taking the derivative, if this is the case, then if I just take the derivative of u, right? If I find u this way and I just take the derivative of u with respect to x, right? I'm definitely going to get p, right? Because if I differentiate with respect to x, right? I'm making basically this point vary right here. My derivative is equal to the integrand in the way I defined. Right? And so u is well defined because it doesn't depend on the path chosen, and because of how I did this, the integral, the derivative will be p. And the exact same thing, right? If you want to do the same for y, it's the exact same idea. Right? Same idea for showing that the derivative with respect to y is equal to q. Right? All we have to do is now pick a path that the last line goes down, is vertical, right? And then, I mean, to not go into the other one, let me do this. Right? And now I make this my path y, gamma y, and I can make, say, this point, right? I can make this point, for example, be my point, right? X, y prime, and I can define u in this integral and then inspect what u is by taking a constant which is given by the integral up to here and then doing the exact same argument from here on. Okay, it's like proof by picture. Okay, and so sometimes we write, okay, so this finishes the proof of the theorem. Right, but I do a bit proof by picture because, otherwise I have to write, if I just keep writing words and words in the board, I don't think that's the best way of visualizing what's going on. But right, if you wanted to actually, prove this with just words, right? If you were writing a proof down and you didn't have the ability, to talk to the person that's listening, right? You know that these paths exist. You know that this is well defined. You define this way. And then you just take the derivative and you see that this derivative will be equal to p, and you do exactly the same thing for q. Okay, so sometimes we write things like this. du is then equal to p dx plus q dy, right? And we call this an exact differential. Okay, and so just before we go, let me just ask a question, right? So this will be one of the central questions we'll answer on Friday. So one of the central questions will be the following. Okay, when is it right? So make sure I use the same notation. When is it that fz dz, right? What is this equal to? This is equal to fz dx plus I fz dy is an exact differential. Right? So when is it that, right? This is what we're actually interested in integrating, right? We did a bit of a detour away from the complex numbers, right, to more familiar real analysis. But really the central question is when we're really interested is in integrating these complex valued functions over arcs. So you want to know when is it that the differential that we actually integrate, right, over, when is it that this is an exact differential, right? When is it that there exists a function u such that this ends up being the first partial derivative and this ends up being the second, okay? So I encourage you to try to think about this, maybe try to work something out, right? If u was such a function, what properties of it can you see? And then on Friday, we'll see that this is very related to functions being analytic, okay? Thanks so much, and sorry for the extra 2 minutes. And I'm around for a while. If there's any questions, I'll just leave all this on. All right, thank you.